In this video, we will discuss how to combine multiple optical devices. The main idea from this section is that the image from one device becomes the object from another device. We already mentioned in the first video that the rays do not always reach the object and can form virtual objects. And the LibreText gives you several examples to learn how to deal with multiple devices, for example, combining a lens and a mirror, or combining two lenses. And so in this video, we will do one more example of combining two lenses together, and we will treat the case of the telescope. The goal of the telescope is to take an object that is very far away and create an image that is larger. And because we use our eyes to look through the telescope, we want the image to be at infinity also. And this is because our eyes don't need to accommodate when an image is at infinity. And so it is more comfortable and less tiring to watch images that are far away compared to watching images that are closer to our eyes. Now, to build the telescope, let's first consider the image that is formed by a convergent lens of an object that is at infinity. So we have a convergent lens, and we place the first focal point f1 on the incoming side. So here, let's assume the incoming side is on the left, and the second focal point f2, we place it on the outgoing side. We have already seen that for objects at infinity, the rays are parallel, and the angle compared with the optical axis represents the size of the object. So the first ray that we can trace is a ray going through the optical axis. We know that a ray going through the optical axis is not deviated. Another principal ray that we can trace is a ray going through the first focal point f1, and such a ray will emerge parallel to the optical axis. Now, these two rays must be parallel because the object is at infinity, and the angle of the rays with the optical axis theta represents the size of the object. Now, with these two rays, we can already find the location of the image, and you see that we find the image to be located at the position of the second focal point f2. We found it by the graphical method, but we can find it also using the formula. Right? For thin lenses, we have 1 over s plus 1 over s prime is equal to 1 over f. And so if the object is at infinity, s is infinite. And so we obtain that s prime has to be equal to f. And so indeed, that means that the image is located at the second focal point f2. Now, the reverse is also true. So if the object is at the first focal point, then s is equal to f, and then s prime will be infinite. And so the image will be at infinity. And this is what we will use to produce an image at infinity so that our eyes don't need to accommodate. So as I said at the beginning of this video, the main idea from this section is that the image from one device becomes the object for the second device. And so if we place another converging lens, the object of this lens is the image that we just found. And if we want the new image to be at infinity, then I need to place the object at the first focal point of the second lens, f1 prime. And so we place the second lens so that the focal point f1 prime is exactly at the same position as the point f2 from the first lens. And if we do this, then the image should be at infinity. So let's trace a principal ray going through the center. This ray is not deviated. And we can trace another principal ray, for example, a ray parallel to the optical axis. This ray must emerge by passing through the second focal point. And so you see that these two rays, they cross at infinity, and so the image is formed at infinity. And so our eyes see this image without accommodation. Now let's talk about the magnification. The size of the object will influence the angle theta. In fact, the bigger the object, the larger theta will be. And you can see that tangent theta will be equal to the intermediate image minus y prime divided by the focal length of the first lens f1. And so the minus sign here is because the intermediate image is inverted, right? Y prime is negative, so minus y prime over f1 is positive, and tangent theta and theta are positive. Now, the size of the image will depend on the angle theta prime. The bigger theta prime, the bigger the image will be. And you see that tangent theta prime will be equal to y prime divided by the focal length of the second lens. So y prime over f2. And y prime is negative, f2 is positive, and so tangent theta prime and theta prime are negative numbers. Now, using these relations, we can calculate the angular magnification. The angular magnification m theta is given by theta prime over theta. And using the small angles approximation, you can replace tangent theta, you can replace theta by tangent theta, and theta prime by tangent theta prime, and you obtain that m theta is equal to minus f1 over f2. And so you see that for our telescope, the angular magnification is negative. And this is because the final image is inverted compared with the object. And the magnification, you can see that the magnification will be larger if the focal length of the first lens, f1, is large, and if the focal length of the second lens, f2, is small.